In the last video, we ended up with this term called miso. So we need to talk about what miso means, right? It's another term that we use in organic chemistry. It's used to describe something very specific, and I think that this you'll be okay with. It's a pretty simple concept, but the problem is that it's a new word, and with a new word, you have to learn the new definition in order to be able to use it and speak the language of organic. Okay, so let's talk about a miso compound. We have talked about, at this point, this definition of optical activity. Okay, so optical activity is this concept that we can put an organic molecule into a polarimeter and that we can have that molecule rotate light. It will either go right-handed or it will go left-handed, right? And we said that the reason that this happens is because these molecules have a chiral center. But there is a chance that we will look at a molecule and we will say, yeah, it's got a chiral center, so it will rotate light. It will either go positive or it will go negative, dextro or levo. So yeah, we can put it in a polarimeter and we'll see it. And then we make this solution and we walk to the polarimeter and we put it in the polarimeter cell and we look through the eyepiece and we see 0. How can this be? I mean, I just spent tons of time making videos telling you that chiral centers will give you R, it will give you S, and if you put it in a polarimeter, you'll get a positive or you'll get a negative. And now all of a sudden, toward the end of this lecture module, I'm going to say, nah, that doesn't happen every time. Sorry. You're going to strangle me right now. But here's why. Our definitions are not changing. Everything that we've talked about before still holds true. But there's exceptions. There's exceptions to everything, right? And the exception here is something called a miso compound. What does that even mean? Okay, well, let's say that we have a molecule that looks like this. I'm going to draw a Fisher projection, just so you will know that we can do a Fisher projection more than just one cross, right? I mean, the longer the carbon chains, the more of those crosshairs that we're going to make in a Fisher projection. Well, it just so happens that this is carbon 1 up at the top. Here's carbon 2 of the chain, and carbon 3 of the chain, and carbon 4 of the chain down here at the bottom. We can do this. Fisher projection's okay with that. It's not a big deal, not a problem. Very common. So this is a Fisher projection that's just a little bit longer. And the reason that we've drawn it this way, folks, let's pick out the chiral carbons. Okay, here we go. This carbon at the top, 3 hydrogens. No chiral. This carbon down here at the bottom, 3 hydrogens. Nope, not at the bottom. What about the 2 carbons in the center? Are those chiral? Well, let's take a look. Up here at the top, we have a methyl group, and then we have a hydrogen, then we have a bromo, and then we have this carbon with all the other crap. So there are 4 carbons, or 4 different groups attached to that carbon. So yes, we have a chiral center right there. Oh, okay, so that's why they did that with the Fisher projection. Well, folks, there's another one too. This 3rd carbon of the chain has a hydrogen, a bromo, a methyl, and carbon with the other crap. There's 4 groups, they're all different, that are attached to this carbon as well. So this Fisher projection is showing you a way, a template, used for more than 1 chiral carbon. This is 2 chiral carbons. We have 2 chiral carbons here. So you would look at this and you would say, oh, look. The question asked me, does it have chiral carbons? And I'm going to say, yes, it does. It does have chiral carbons. Right here is one of them, and right there is one of them. So check. Part A has been answered. Part B says, based on that, do you think optical rotation is going to happen? And you would go and you would look at the structure and you would say, yes, because it's chiral. I don't know which way it will go. It could go positive. It could go negative. I just don't know. But yes, it does have optical activity. And that would be your answer for B. And then you would turn that in and you would get that answer wrong. Why? It meets the definition. Why? That's because it's a miso compound. So what does miso mean? Miso means that you can draw what we call a plane of symmetry. Remember this term racemate? And I said a racemate is like a mixture. It's a 50-50 mix. So you've got some that rotate one way, you have some that rotate another way, and both of those together almost kind of cancel each other out, right? This was a concept that we introduced very early on. Well, miso compounds are very similar. Miso compounds means there's a plane of symmetry. That means you can cut the molecule in half. When you do that, they will overlap each other. What does that even mean? Look at this molecule that I've just drawn here. I can create a plane of symmetry that's right here, straight across. I can also go up and down if I need to, but here is a plane of symmetry. And what that means is think of this as a fold on a sheet of paper. If you drew this on a sheet of paper and you cut out around this molecule, right? Is there a way that you can fold that sheet of paper on itself to make these things overlap and stack on top of each other perfectly the same? Yes. Therefore, it's a miso compound. Because if I fold this drawing at that seam that I've just drawn, my two bromos would overlap, wouldn't they? They would be stacked on top of each other. My two hydrogens would overlap, wouldn't they? They would be stacked on top of each other. These two carbons in the center, they would also overlap and stack on top of each other. And then this methyl group on top and this methyl group on the bottom, those would also overlap when I create that fold. So everything matches and they cancel each other out. That's kind of the concept here. That's a miso compound. Now, you don't have to do the crease left and right like we did here. It doesn't have to be a horizontal crease. It can also be a straight up and down crease as well. That's perfectly okay with it. That's also a miso compound. Well, because of that, even though this molecule has one chiral carbon at the top and one chiral carbon toward the bottom, even though chirality is present, this molecule is not optically active. And again, the reason, there's a plane of symmetry. So this is a miso compound for that reason. Let's look at another. Here we have a carbon and a carbon. And then off of this carbon, I don't know, let's do a CH3 group here and a CH3 group here. And then here, let's do a solid wedge with a bromo group. And here, let's do a dashed wedge with a hydrogen. Here, let's do the same thing, solid wedge, bromo group, and then here, dashed wedge, and a hydrogen. Part A of the question, does it have chiral carbon? And the answer is yes. You know that this one's not one. That's 3 hydrogens. You also know that this one's not one, 3 hydrogens. This carbon is chiral, 4 different groups, methyl, hydrogen, bromo, and carbon with the other crap. Over here to the right-hand side, that one's also chiral, methyl, hydrogen, bromo, carbon with the other crap. I have 2 chiral carbons that are here. So part B of the question, will it show optical activity? And you might have a tendency, especially in the past, to automatically say yes, it does. There's chiral carbons. However, this is a miso compound. There's a plane of symmetry. And this time the plane of symmetry is going to go vertical. I can cut this molecule out on a sheet of paper, and I can fold at this crease right there. I can fold that molecule onto itself, and everything is identical. The methyl groups will touch when I fold that over. The carbons will touch when I fold it over. The hydrogens will touch when I fold it over. And the bromos will touch when I fold it over. The hydrogens are pointed in the same direction. The bromos are pointed in the same direction. Everything is identical. There is a plane of symmetry in that molecule, and that is what we call a meso compound. Let's take a look at another example. Let's figure out if this is meso or not. I'll do a CH2CH3, and then we'll draw a line, and I'll do another CH2CH3. Looks pretty good for now, right? Okay, so here, let's do a Fisher projection with an OH here and a hydrogen there. And up here at the top, let's do a Fisher projection with an OH here and a hydrogen there. But here in the center, let's do another chiral carbon. Well, not chiral. Let's do another carbon. And let's have this to be a CH2 group right there. So, if I want to replicate that in the same way that we've done before, hydrogen here, hydrogen there. So not chiral, but it's a middle carbon. Now the question, is that a meso compound? Is there a plane of symmetry that's here? Hopefully you're going to tell me yes. Because that plane of symmetry can go through that carbon right here. Just so happens to be a perfectly middle carbon in that structure, and that is perfectly okay. If I cut that molecule out on a sheet of paper and I fold it in half at that position, well, that carbon and the two hydrogens, they really don't count. They're not part of the folds, are they? No. However, everything else will overlap. This carbon at the top and this carbon at the bottom will match. The two hydrogens will match. The two OHs will match. The CH2CH3s will match. So even though we get this weird kind of middle carbon man right there in the center, that's perfectly okay. We can draw the line of symmetry through that, and we will be perfectly fine. Therefore, this is a meso compound. We have a chiral carbon that's there. We have a chiral carbon that's here. But those chiral carbons do not make this molecule optically active because it is a meso compound. So let me give you one more example of a meso compound. Again, these are the exceptions, right? Let's do a cyclopropane. And then off of this, let's do an OH pointed towards you. And we'll do an OH pointed towards you here. And then this needs a fourth bond. We'll do a dashed wedge to a hydrogen and a dashed wedge to a hydrogen. Does this have a plane of symmetry? Well, if you cut that molecule out and you try to fold it, either vertical or horizontally, will you be able to get everything to overlap? And the answer is yes. This is also a meso compound. And the way that you could fold it is right here in the middle. If you fold it at that crease, this piece of the triangle lines up with that piece of the triangle. This piece of the triangle lines up with that piece of the triangle. The two hydrogens will line up. The two OHs will line up. They are both pointed in the same directions. Everything is identical on either side. So yes, this is a meso compound. We have a chiral carbon that's here. We have a chiral carbon that's there. Chirality's at play. We can get an R or an S. We can also get an R or S on the other one. That's not a big deal. But it will not give us optically active data. When we put it into a polarimeter, we will not get positive or negative. No. So R and S we can still assign to these. That does not go away. That does not change, folks. But optically active will change on us. And meso compounds cancel it out. One more term I would like to introduce is something called Pro-Chiral. We've seen this idea of chirality, which is a carbon with 4 different groups, right? So here I'm going to write X, Y, Z, and A. I don't know, 4 random variables. They're all different. So this is chiral, okay? Then we also have something called achiral, which is a carbon that does not have 4 different groups. So let's just say we have a hydrogen, and maybe a chlorine. I don't know. I'm just making it up. So there's no 4 different groups on that carbon. It's not chiral, and we've termed that achiral. Well, there is a special term. Some people use it. And this special term is called pro-chiral. All right, so pro-chiral is basically a carbon that's attached to 2 different groups, X and Y maybe, but along with this are 2 hydrogens. Kind of special. Because if we can take one of these hydrogens and delete it, get rid of it, and replace it with something else that's different, we would have a chiral compound at that point, right? So you're almost at chiral. And that's what pro-chiral means. This is like at the end of the semester, and I start giving you a cumulative average, and you look at your average, and you're like at a 90, and 92 is an A, and you're looking at this 90, and you're like, oh, almost, I'm almost at an A. I'm almost at chiral. Well, that's how close this is, right? So if I could delete the hydrogen and replace it with a different group, then that would be a chiral compound at that point, which makes this setup pro-chiral. Something else I also want to mention, because it's something that they like to do to you, hydrogen has 3 different isotopes. We have normal hydrogen, which is H1, and then we also have H2. This is a little heavier of a hydrogen, a little fatter of a hydrogen, and this is called deuterium. Deuterium is used for many different purposes in the lab, and deuterium has a symbol of a D. So sometimes they will give you these structures in these example problems, and they will put D's on here. And you're looking on the periodic table and you're like, what in the world is D? I can't find a D for an atomic symbol. What does D stand for? D stands for deuterium. It is a heavy hydrogen. It is a fatter hydrogen because of extra neutron number. And we can radio label molecules using deuterium. And we can track the movement of deuterium to see how reactions are taking place. It's one of the common things that we do in order to figure out how mechanisms happen, right? All those curvy arrows and reactions of alkenes and alkynes. How do we know that that's really for sure what goes on? We radio label them. And when we do, we can track where these weird isotope of atoms happen and where they end up. So if you do see D, that is what D represents. It represents deuterium. We also have H3, not used as much, but of course that's called tritium, something else that we've talked about before. Tritium, tri means 3. Sometimes they use that as a T. However, they rarely will put that into a question. But they do tend to use deuterium quite a bit with some of these examples. So we do treat that differently. We do look at this as a different group, okay? So with this particular carbon, I have a group that's here at the top. It's a different group on the bottom. We have a hydrogen that's here to the right, and this is deuterium. It's not really hydrogen. We regard that as a different group, so therefore this would be chiral by definition. So if the D's are there, you do treat it differently than a regular hydrogen, okay? Now, Let's go back and think about reactions. All of those reactions that we talked about with alkanes and alkynes. We can predict products for them, right? We know how to do that. Double bond breaks. Remember that? I'm sure you do. Or triple bond breaks down to a double. Then the double bond breaks down to a single. Folks, all of those will generate products. We know that. We've been writing them down. We've been predicting them. We've been naming them. All of that was all involved in the alkyne and alkene reaction modules. One of the things, though, that we didn't really pay attention to is how things are added onto those molecules. Some reactions are very specific, meaning, how do they add? Do they add on the same side of the molecule? Do they add on different sides of the molecule? That's something that we really haven't paid attention to in the past. But it is part of reaction. It is part of predicting products if I want to go to that kind of detail. And it really does give me minor and major products. So just when you thought it couldn't get any worse, I can take a triple bond, I can break it down to a double, then I can break it down to a single, I can give you that product, I can name that product, and then I can look at that product and say, are there any chiral centers? If so, let's label them. And then I can say, now draw the R's and draw the S forms. And then I can say, which one of these is actually going to be preferred? The R form or the S form? That we haven't done, and we're not going to do that right now. But this is part of reaction theory, and I don't want you to kind of forget about that. There's even more detail that we can go into with those reactions if we want at any point in time. Very similar to the hydrogen mechanism. Do you remember the H2 and then platinum, right? And H2 and platinum took a double bond and it broke it and it completely destroyed it. And I said, hey, the hydrogens are added onto the same side of the molecule. And then we looked at triple bonds and we said, well, you know, we can do H2 Linlar, and H2 and Linlar will take a triple bond down to a double, but the hydrogens get added on to the same side. But if we didn't want to do that, we could use basically sodium and ammonia at a really cold temperature, and that will maybe put things on opposite sides. Look at what we were talking about during that time. We were talking about stereochemistry. We were talking about cis, we were talking about trans, and that's stereochemistry, folks. That's the field. We've just focused on a certain half of stereochemistry because cis and trans and E and Z were something that we have already talked about. But that is stereochemistry. We already alluded to it a little bit. But now, we know that any of those reactions can form a product. And those products could have chiral carbons. And those chiral carbons, we can go and talk about R forms and S forms of those structures. Just a couple of more slides I want to do before I stop this video. Again, here is a generalized summary of what we've been talking about. Here we have a molecule to the left, tartaric acid, a great acid in wine. I mean, this is going to be coming from grapes. It's naturally occurring. It's one of the acids that we do find in wine. It's one of the ways that we can rank the quality of wine. So tartaric acid, there's its structure. Notice shaded or dashed wedges. And if I do a mirror image of this, just flip it around. That's all we do, folks. We have an enantiomer. Well, if I look at this structure, do you see how this OH is on a dashed wedge and this OH is on a dashed wedge? Okay, well, if I flip one of those around, not both, but just one. So I leave this OH as is, but I flip this one. No longer is it dashed wedge, it's now a solid wedge. Well, because I didn't take an exact mirror image, they're still stereoisomers. They're still related. They're cousins. This is called a diastereomer. Same thing happens over here with this enantiomer. That enantiomer, I've flipped only one of the OH groups and that's it. So therefore, the one to the right and the one down below are also diastereomers of each other. That is the term of diastereomer. However, folks, this is also a meso compound. I can create a plane of symmetry and fold it on top of each other and create a mirror image, basically. So if I put it into a polarimeter, it's not going to give me any optical activity at all. All right? So there's the relationship between these three terms that a lot of people just get completely confused with. Another thing I want to show you is Vicks and Heller. Why? Why is he showing me Vicks and Heller? What does this have anything to do with RNA? Everything. Because, folks, look at to the right-hand side. The active ingredient in Vicks and Heller stick is right up here at the top. It's got some stereochemistry associated with it. Pretty simple compound, actually. It's a benzene ring with a carbon chain, and we get this NH group over here on the right-hand side. Well, right here we see a chiral carbon. I know that's probably a chiral carbon because I see the dashed wedge. Right there it is, okay? So that dashed wedge has to go to something. Well, if it's not drawn, what is it? I think you can give me that answer. And if we flip that stereochemistry right there, we go from Vicks and Heller stick to methamphetamine. That's meth, folks. That's the only difference. You remember the thalidomide story? Thalidomide, RNS, optical activity, rotation, chiral carbons. One was good, one was bad. Look at here. Same concept, same deal. We have a molecule on top. That molecule is exactly like the molecule down below. One is sold legally in a store, and one is made illegally in a garage. The only difference is the direction that that methyl group is pointed to. Oh, methyl group. That's right. And look at this word, meth. What do you think that stands for? It's a methyl group. That methyl group is very important. If it points away from me, it's sold in a store in terms of Vicks. If it's pointed toward me, same group, same molecule, same everything, except the orientation, then all of a sudden it's methamphetamine. My teeth are going to rot out. I'm going to scratch and dig because I think there's bugs all over me. I probably will end up in jail if I get caught. And if I'm trying to make it, I probably will end up blowing up my garage or whatever kind of outbuilding that I'm trying to make it in. Very dangerous stuff, right? But all due to stereochemistry. That's what's crazy about this. Who would have known? So to sum all this stuff up, as far as the definitions go, folks, here we go. Up at the top, we've talked about isomers. This is nothing new to us at all, right? We've been talking about isomers for weeks and weeks. And there's two different types of isomers that we have now encountered. Over here to the left are the constitutional ones. This was like the isopropyl group, the sec-butyl group. The questions that said, hey, you've got 6 carbons. How many different ways can you connect 6 carbons to give me a different structure? But notice what that was. How can you connect them differently? That's constitutional isomer. Over here to the right-hand side, these are stereoisomers. That means they're connected the same way, but they're pointing in different directions. Well, under the stereoisomer category, there's 2 more. There's ones that we call configurational, and there's ones that are called conformational. Configurational would be things like your double bonds. They're kind of static. That double bond cannot move. That double bond cannot change. Those groups get locked into place. And this is where we get things like cis and trans and E and Z. Those are configurational isomers. Conformational isomers, these are rotations about single bonds, but this is where the world of R and S belong to. Those are conformational. It also talks about amine inversion. Don't really look at this. This is nothing for us right now, so I'm going to cross it out. But if you need a nice flow chart to kind of just put in perspective what we're talking about here, there you go. Under stereoisomers, under the conformational isomers, under the R and S, this is where we get the word enantiomers. It's also where we get the word diastereomers. It's also really going to lead us to meso compounds as well, even though they can happen somewhere else. But meso compounds typically fall into that category. So this is a very good summary or flow chart on the different types of topics that we've talked about at this point. And that's where my full lecture is going to stop. Can you believe it? This might be the shortest lecture module that we've had so far. But there could be one more video left. And what I've decided to do is to go through and answer some questions for you, just to do some more example problems. You know, it seems like we've done examples, but I don't maybe quite feel comfortable with that yet, right? It seems like all of these different kind of topics and ideas were presented. We did an example here and an example there and an example here. But, you know, maybe I just need to kind of condense it all together and just work out some example problems, maybe from the textbook, just to reconfirm that you know what you're doing. So that's what you're going to see in the next video, which hopefully will be the last video of this lecture module. So stay tuned. You're almost done. Crack those knuckles. We're going to be working them out. Until then.